Look at the center of the dial, the blue circle right in the middle of everything, that's Earth. And everything else, the sun, the moon, the stars, all of it is orbiting around us. That clock is 600 years old, the oldest working astronomical clock in the world. And it's wrong. The man who proved it worked here in this city.
My name is Lilith, and today I'm here to tell you about a great astronomer, the father of modern optics, the person who first correctly explained how the human eye works, a founder of the mathematics that became calculus, and somehow the person who wrote the world's first science fiction novel.
His work also helped me get here using GPS, but one thing at a time. The Earth is at the center of everything. For 2,000 years, that's what every educated person believed, because it's exactly what it looks like. Every single day of your life, the sun rises, moves across the sky, and sets. You feel completely still. The universe moves around you. Then people started noticing details that didn't quite fit this picture.
If you go outside on a clear night, track where Mars is against the background stars, do it every few weeks for about 2 years, you will spot it too. Most of the time it drifts steadily in one direction and then it stops, reverses, moves backwards for weeks, then stops again and continues forward as if nothing happened.
This is called retrograde motion, and to ancient astronomers it was the most disturbing thing in the sky, because there was a rule nobody questioned for 2,000 years. The heavens are perfect. The circle is the only perfect shape, so everything up there moves in circles at constant speed forever. And a planet that randomly reverses direction doesn't really fit the picture, like at all. So astronomers did what people often do when reality doesn't fit the model. No, they didn't change the model, they added complexity on top of it.
Circles riding on circles, epicycles they call it. A planet moves around a small circle, while that small circle's center moves around a bigger circle around Earth. Tune the sizes just right and you can reproduce retrograde motion. By the 1500s, the official picture of the universe needed dozens of these nested circles, different rules for every planet, patches on patches on patches.
And it worked. Well enough to build calendars, predict eclipses, build clocks like Orloj, but nobody knew why it worked. It was a description of something, not an explanation. In 1600, a 28-year-old mathematician named Johannes Kepler arrived in Prague. Nearsighted, frequently sick, broke. He had left his teaching post in Graz under pressure because Protestant astronomers weren't particularly welcome in Catholic Austria, and traveled nearly 500 kilometers to take a job as an assistant to the most famous astronomer alive,
a Dane named Tycho Brahe, freshly appointed imperial mathematician to Rudolf II, Holy Roman Emperor.
The invention of the telescope is still 8 years away, so Kepler and Tycho were working with nothing but their eyes, their instruments, and time. And Tycho had used that time well.
For over 20 years before Kepler's arrival, he had tracked the planets night after night, using enormous brass instruments, quadrants, sextants, some the size of small rooms, mounted on walls, and turning mechanisms of his own design. His measurements were impressively accurate to about 1 to 2 arc minutes.
An arc minute is 1/60th of a degree. Your pinky at arm's length measures 1 degree. Now divide that by 60.
That's Tycho's margin of error. No telescope, 1580s. Naked eye, through brass sights, written down by candlelight.
It was the most detailed, most precise record of planetary position ever assembled by any human being up to that point in history. And Tycho gave Kepler one task: use this data to figure out the orbit of Mars. And his findings changed everything.
At this point, it's important to note that Kepler believed Copernicus was right, The planets orbit the Sun, not the Earth, which in 1600s was genuinely dangerous.
Kepler also believed orbits had to be circles. Heavens are perfect, remember? Nobody was questioning it. So he takes Tycho's Mars data and starts fitting circles.
Off-center circles not centered on the Sun. He tries one configuration. Check it with Tycho's data. Close. He adjusts. Check again. Closer.
After roughly 4 years of work, partly inventing new calculation methods, he finds a circle that matches almost every single one of Tycho's Mars observations. Almost. One point was off by 8 arc minutes. To any other astronomer in history, this is nothing. Tycho's instruments wobbled that night. Move on. But Kepler knew Tycho's work. He knew Tycho was never off by more than 1 or 2 arc minutes, not in 20 years of observations. So 8 wasn't noise, 8 was a message.
And Kepler wrote that these 8 minutes of arc could not be ignored, that from this small gap a full new understanding of the heavens would open up.
Kepler decides the 8 arc minutes are real. And if so, the circle, that perfect heavenly shape, has to go. So if the orbit isn't a circle, what is it? Kepler tries other shapes and eventually, reluctantly, because to him it felt inelegant, almost embarrassing compared to a circle, he tries an ellipse.
An ellipse has 2 focus points, not one center. Kepler places the Sun at one of those foci, off to the side. And Mars's orbit fits. All of it fits. You see, Mars has the most elliptical orbit of any planet Tycho had good data on. If Tycho had assigned Kepler almost any other planet, for example Venus, whose orbit is nearly a perfect circle, that gap would have been too small to notice.
The entire revolution in our understanding of the solar system may have depended on which planet Tycho happened to hand to his new assistant. This became Kepler's first law, published in 1609, in a book called Astronomy Nova, the New Astronomy. Planets orbit in ellipses. The Sun sits at one focus, not in the center. For the first time in 2000 years, someone looks at the skies and says, "This isn't perfect." But Kepler found something else inside that same data. If the orbit is an ellipse, the planet's distance from the Sun keeps changing throughout the year. And Kepler noticed, closer to the Sun, Mars speeds up. Further away, it slows down.
He described it using areas. Picture a line connecting the planet to the Sun. As the planet moves, that line sweeps across a region of space like a clock hand across a stretched, distorted clock face. Kepler found that this line always sweeps equal areas in equal times. Near the Sun, the planet races to keep up. Far away it drifts. The area stays constant.
So not only was the shape of the orbit wrong in the old model, but the idea that planets move at constant speed was wrong too. Another piece of perfection gone. And this is Kepler's second law. Every satellite in orbit above us, from weather satellites to GPS, follow elliptical orbits and change speed exactly the way Kepler described. The engineers who calculate satellite paths are at their core, using geometry worked out by hand 400 years ago in this city, in the building behind me. A decade later, in 1619, Kepler published one more law, and this one is the strangest. He found a relationship between how long a planet takes to orbit the Sun and how far away it is.
The square of a planet's orbital period is proportional to the cube of its average distance from the Sun. In plain language, if you know the distance, you can calculate how long a year is on that planet. And if you know how long a year is, you can calculate the distance from the Sun.
True for Mercury, true for Jupiter, true for every planet in our solar system, and true for planets we have never seen around stars we will never visit.
When astronomers detect an exoplanet today, a planet orbiting another star, thousands of light years away, they usually can't see it at all. What they detect is a tiny repeating dimming of the star's light as the planet passes in front of it. That repeating cycle is the orbital period. And Kepler's third law is the equation they plug that number into to calculate how far the invisible planet sits from its star, whether it might be warm enough for liquid water, whether it is able to have life. There's a space telescope named after Kepler, the first mission ever built specifically to hunt for planets around other stars. By the time it retired, it had confirmed more than 2,700 worlds beyond our solar system,
using the law he found because of 8 arc-minute error in 17th century Prague. 70 years later, Isaac Newton finally found the answer to the question why Kepler's laws work. He proposed gravity,
a force pulling any two masses together, weakening with a square of the distance between them. And when Newton did the math, asked what shape of orbit this force would produce, the answer was an ellipse, with a larger mass at one focus.
Kepler's laws weren't just good description, they were the mathematical fingerprint of gravity itself. As I mentioned, Kepler started his journey towards 3 laws, which are still in use today when telescopes didn't exist yet. In 1608, Hans Lippershey, a German-born spectacle maker working in the Netherlands, applied for a patent on a refracting telescope he called a schikker, looker from Dutch. His claim was denied after other instrument makers came forward with similar devices, but word of the invention spread quickly across Europe. Galileo built his own improved version in 1609, and by 1611 the Greek scholar Giovanni de Misiani had given it a name: telescope, from the Greek tele, far, and scopein, to look. When Galileo pointed his telescope at Jupiter and wrote exactly about what he saw, Kepler wrote back, and within a year had published a complete mathematical explanation of how the telescope actually worked. Not just a description, the actual geometry of how lens bend light to form magnified images. Nobody had done this before. Not even the people who invented the telescope understood why it worked.
Kepler then redesigned it. His version, 2 convex lenses instead of 1 convex and 1 concave, gave better magnification and a wider field of view. The design still used in most refracting telescopes today is his.
He also, in that same period, published the first correct explanation of how the human eye works. Before, the dominant theory, going back to ancient Greece, was because rays came out of the eye and touched objects, like eyes were lanterns.
Light enters the eye, the lens focuses it, an image forms on the retina, and the brain reads it. That explanation, fundamental to everything from optometry to camera design, is Kepler's.
This is why he is formally recognized as the father of modern optics. And in addition to all that, Kepler found time to write a novel.
It's called Somnium, The Dream. It tells the story of a young astronomer who travels to the moon, carried by a spirit, and describes what the universe looks like from the lunar surface. The Earth rising, the stars unblinking in an airless sky, the slow rotation of the moon, the alien landscape.
Every single astronomical detail in that piece is correct. Carl Sagan and Isaac Asimov both praised it, and it is widely considered the first work of science fiction ever written. I don't know what to do with this information, but I think you should have it. You know what I like most about topics like this? You can clearly see how all the sciences work together. Astronomy, mathematics, optics, physics. Kepler didn't work in one field, he worked in all of them simultaneously, because to him they weren't separate fields. They were different windows into the same universe. Thank you for your time. See you in the next video.